Hey there, math fans. This is a motivation video for someone just starting with Taylor series. At the University of Washington, we teach Taylor series in a way where we do error bounds, do some technical stuff, and then we talk a little bit about applications, but we don't get very deep. And that often leaves students with the feeling of, why am I doing this? So I have a series of videos where I talk about interesting applications. And if this is interesting to you, you can check those out more. But for this video, my intentions are to just give like a quick intro. These are all examples. I'm going to do several quick examples, try to keep it short, from a project sheet I made to try to get, answer this question. Students have asked me a lot. Now, this particular integral, just as a quick example, I'm going to use Wolfram Alpha to do sort of a quick version of this. So I'm kind of doing something where I'm assuming we don't know very much about this yet. This integral can't be done with any of our techniques from Math 125. If there's an x here, it can be done with substitution. If there's not an x, it's actually a well-known integral of something we can't do very well. So what do? We can approximate with Riemann sums, and that works pretty well. But another way is try to replace this with a polynomial. You might say, well, how can we do that? It's not a polynomial. Well, you can try to get the Taylor series. That's what the Taylor series is. Taylor series for e to the x squared. Some people are like, well, what's a polynomial? But I'm just going to use Wolfram Alpha. I'm going to just use an online calculator. I said Taylor series for e to the x squared. Oh, look, it gave me it. It says this is an approximation. 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6 plus x to the 8 over 24 plus things of order higher than the 9th power. You can click more terms and it gives you more. That's what we're going to learn, is how they're generating that. That's really valuable. So what that means here is you can say, well, this is approximately, now there's a lot of things to talk about, like, is this a good approximation? But it is. It's a very good approximation. But this gives you the first few terms. Now, we're going to have a way to get those terms easily from a pattern. We won't need a calculator to get it. This is a well-known series. But let's just say we stop right there. Then you can integrate that instead. Now, that can be integrated by hand, and you can even find the pattern. It's x plus 1 over 3x cubed. And this is the sort of stuff that a calculator might do. A method, not necessarily this method, but some method of approximating. This is going to be 6 times 7, so 42, x to the 7th. Let's just stop there, 0 to 1. And so I can say that this integral is approximately 1 plus a third plus a 10th plus a 42nd. Now that already, if you sort of keep going, so it's going to be 1 plus a third plus a 10th, and you can see each number is getting smaller. Let's just see what that is so far. So that's 1.43. Okay, you could add another one. Plus 1 over 42. That's 1.45. So at this point, I'm pretty confident the answer is about 1.4 something. So you can see that can be done pretty quickly and done sort of by hand. Now the next one's going to be, when I integrate, it's going to be 1 over 24 times 9. So we'll add 1 plus 1 over 24 times 1 over 9. And what's valuable about this is not just approximating particular things, it's the whole analysis idea. And sorry, I'm not looking carefully at what I'm showing you. So this one is 1.46. And so you could just go a few more terms, and you could then say, okay, the digits are leveling off. I got it. That is a huge general type of thing we can do with Taylor series. There are other types of series that involve, series means sum. So and a Taylor series means the sum of polynomials, meaning powers of x. We really like those because we can integrate them fairly easily. There's lots of good techniques to work with them and solve with them, approximation techniques. Okay, so that's our first example. So I'm going to grab a couple others from my example sheet. to, like I said, usually this is stuff I just mention to the students. I'm going to try it as saying it up front. So this is something I don't know very much about, but it's an example I found many years ago. This is the formula for kinetic energy in Einstein's theory. So accounting for whatever relativity, or again, I should not be lecturing on this at all, but this is the speed of the object. This is the speed of light. But this is a messy formula. So some people have asked, well, what if we approximate that with polynomials? So let's play that game right now. I want the Taylor series for 1 over the square root 1 minus, and usually what we do is we think of v and over c as one thing. So I'm doing a little bit of stuff to try to simplify my work a little bit, but this is going to be, let's think of this like this. And that's part of some of the challenges of using Taylor series. So let's do let's throw in the -1 too. What's the Taylor series for that? So let's see what Wolfram alpha tells us. And I should make this a little bigger so we can see it better. Oh, it doesn't understand my query. -1. See what it says. Oops. Let's try it without that. I should have planned this a little better. Taylor series for this. Oh, I did say Taylor series. Oh, there it is. There's the first few terms. Okay, so what does that say for me? And I didn't include the -1. Okay, so I can subtract off that first one. So it says the first few terms are going to be, for all of this, the following. So the 1 will cancel. I'll have a 1/2 t squared plus a 3/8 t to the 4th, and then higher order stuff. Now, if the thing inside the parentheses is small, this is going to be a pretty accurate formula because you're going to be keep raising it to higher powers. And if you take a number between 0 and 1 and keep raising it to higher powers, it gets really small. Okay, so this is v over c. V over c. So sometimes people say, okay, if your speed is much smaller than the speed of light, then this is a really small number. In which case, these are dramatically smaller than the rest. And this is a sort of argument people make, is they say, we can ignore these, and that happens a lot in science and physics, and replace that entire big mess by the following. m0, c squared, and then 1/2 v squared over c squared. And the c squareds cancel, and you get the Newton's formula for kinetic energy. So that's why when we say things like Newton's formula approximates Einstein's formula, this gives us a precise way to say that. So that's different than just what a calculator does. It's like an analysis tool. So I hope that was kind of interesting to you. This is how I think about Taylor series, not about it being a calculator. Those are just simple examples for us to do. I think about it as a general analysis tool, a way we can attack all functions in kind of a uniform way. Okay, so last couple things. This might be of less interest, but it can be used to evaluate infinite sums. So once we have, I'm going to shrink this back down just for a second. Once we have a collection of known Taylor series, which we will have, and they're not that bad to find, we'll have the following. That this equals 1 plus x squared. We'll be able to plug numbers into that. In fact, that's what's happening here. A 1/5 is being plugged into this. And so if these two things are indeed the same, then you can say this is the same as 1 over 1 minus 1/5 is 1. And the notation scares people. But I would argue that it's pretty darn interesting that we can figure out what this is approaching. And it's approaching 1 over 4/5. So it's approaching 1.25. All of these other ones are also approaching things. This is approaching e to the 1. That's approaching e. I think that's amazing. This is approaching e squared. This is actually approaching cosine of pi, which is -1. This is actually approaching all over n. Oh, I think that's log of 2. Apologies if I have that wrong. I didn't prepare this piece. All of those are just plugging into known patterns. I found that really interesting when I was a student. I have found that other students don't always find that interesting. They're like, who cares about infinite sums? Now, those things do come up in lots of applications, but you're not going to see that till future courses. So sometimes it's hard to find examples that would excite calculus students. I find this one pretty interesting because by the time students are in this course, they've solved a little bit of differential equation. So let's just give a differential equation we already know the solution to. dy dx equals y with y of 0 equals 1. That's when you solved. It's separable. You did it in Math 125, and your final solution was this. That leads to an exponential model. So an interesting thing that we saw there was the only reason we could solve that is because it was separable. So what do we do if it's not separable? Well, we can try to find its Taylor series. Now, the Taylor series for this one is known. It's 1 plus x plus 1 over 2x squared plus 1 over 6x to the third plus 1 over 24. And there's a reason I know those numbers, but I'm going to save that for the course. Okay, so one way to solve something like this is to just say, well, I'm going to try to find the Taylor series. I'm going to try to find these numbers. And this I found, back when I was learning differential equations, I found this to be the most intuitive way to solve. So you say, well, if I plug in 0, what do I get? This has to be a 1. That's from the initial condition. And then you just build from there. What do I mean build from there? Well, you can actually write down what the derivative looks like. Because we're thinking of these as numbers. This is going to be 0. This is going to be a1. So if everything's a polynomial, then a lot of this stuff becomes kind of nice. And you just basically plug into both sides. You say, well, this is the derivative. And the derivative is 0 plus a1 plus 2a2x plus 3a3x squared, blah, blah, blah. And the other side is just the function. So it's 1 plus a1x plus a2x squared. And then you match up the sides. Well, since this is 1, and this is the only constant on the other side, that means, so we had a0 has to be 1 because the initial condition. We have a1 has to be the same as a0, which is 1. And you just play this little game. But that means that this is 1. And that means these two things match up. So that means that 2a2 has to be a1, which means that a2 has to be a half. And then you just keep going now that I know a2. And I remember as a student thinking, oh, I get this. It gives me a general way to find a function. This means that a3 has to be a 6. And I remember on a final exam, I forgot the appropriate method to solve, but I got the first few terms, and then I recognized, I was like, oh, I know that function. And then I had the answer. So this idea of thinking of functions in a general way, a general uniform way, is a powerful idea. That's why other departments want you to see this and learn the series for the basic functions. Okay, I hope that gave a little bit of motivation. In class, we'll start with error bounds to get us to believe that this does approach, like that the ... makes sense here, that we can keep going and we get closer and closer. That part's not necessarily that fun. And then we just talk about manipulating when we get to the end, but I hope that motivates you and shows you why this might be interesting in courses that follow this. All right, thanks for listening.